Hello everyone, welcome to my presentation. My topic is about range communication and sensing. The ever-increasing of the number of wireless technologies makes frequency distribution a daunting task. Therefore, researchers have been thinking about a solution to combine different wireless technologies so that they can use a single frequency. When it comes to communication and sensing, there are natively two different wireless technologies using two different frequencies. So the goal of this GCase is to combine them so that they can use a single frequency. At the end, we want to save frequency hardware costs and to get an intelligent network in some applications such as autonomous vehicles. So how GCase works? We have a communication and sensing blocks which are combined in a single hardware. The communication block sends a communication signal through a channel which contains some objects such as cars, buildings, trees, and so on. The first part of the signal is reflected back to the sensing block, and the second part of the signal is received by the communication receiver. Then the sensing block has to estimate the real channel, and from the estimated channel, the range velocity engine outputs an image which contains all the targets in form of points, which indicate the range and the speed of each target. So the first step of our work is to improve this classical scheme by first adding a precoding block which will improve the autocorrelation property, and then to reduce the range velocity engine complexity using sparse computation. The second step of the work is to use a deep convolutional neural network to have an advanced features extraction and range velocity engine improvement. This is done in two steps. The first step, which is a training step, use the estimated channel and the range velocity image to train a convolutional neural network. And at the prediction step, whenever we have a new estimated channel, we don't need to go through the range velocity map engine anymore. We just have to predict the range and velocity image using the train model. By using our schemes and algorithms, we can reduce the velocity and range estimation error and then improve the range and velocity image quality. In the previous steps, the channel is static, which means that at each communication step, we send the same number of frames. But it's important to mention that when the number of frames increases, the communication becomes bad and the sensing is good. Inversely, when we decrease the number of frames, the communication becomes good and then the sensing is bad. So the question is how many frames to send at each communication to balance between good sensing and good communication. This number of frames will depend on the previous estimation and also the current state of the environment. This is what we call a dynamic waveform and communication and sensing optimization. So the output of this research is an alternative way to mitigate frequency congestion. Thank you for your attention.